Hello, I'm Hashi from Wanted to Read Japan. Today I'll be talking about off-policy evaluation and learning for matching markets. Recommender in matching platform are different from standard recommenders. In EC platform, if a user buys an item, it is a success for a recommender. In matching platform, it's two stages. Let's focus on the job matching setting. We show a job seeker, and the company may send scout, and then job seeker may reply. Mutual preference are necessary for a successful match in such a matching market, and this two-stage mutual process is lead to the positive label sparsity. This is an important point in our paper. Let me start with formalize our problem. The policy recommends a job seeker J to company C with probability pi C, and company may send scout message to job seeker with probability QS, and job seeker reply with probability QR. Using this, the policy value is represented by the following formula. This is the expected number of matches under the policy pi C. We want the policy that maximizing a policy value. But if you can estimate this policy value accurately from past interaction data collected under an existing policy, we can evaluate new policy without costly or risky A/B testing, and we can run higher performance models by maximizing estimated policy value very hard. But how can we know if our estimate is reliable? We use two metrics. First is the mean squared error, MSE, that tells us how close our estimate is to the truth value by balancing bias and variance. Second, error rate addresses more important and more practical issue. When comparing some policies, how often would we pick the worst one? Various estimators have been proposed so far for off-policy evaluation, but they are originally developed for non-matching problems. Direct method predicts matching probability QM has directly, and it has low variance, but it can be biased if the predictor is not accurate. Inverse propensity scoring uses importance weight pi over pi 0 to correct the distribution shift between new policy and existing policy. It can be unbiased, but it often has large variance. Doubly robust combines DM and IPS and achieves better bias variance trade-offs. Let's focus more on importance weight used in IPS and DL. It is powerful because it is unbiased, but it often has extremely high variance, especially when the number of actions is large or reward feedback is sparse. Unfortunately, both are common in matching platform. So we propose two novel estimators, DIPS and DPR, for matching markets. In this presentation, we focus on the evaluation method, but running method follows the same principle as its details in our paper. Let me start with DIPS. The main idea is very simple. We decompose two rewards separately. That is, decompose matches into scout sending and replying. Scout sending level is relatively dense, so we use its IPS to provide unbiased estimate with importance weighting. In contrast, replying level is very sparse, so we use its DM to mitigate the variance problem. The DIPS shows large variance reduction compared to the IPS due to this reward separation. It slightly has bias, but achieves lower MSE due to the better bias variance trade-off, better bias variance controls. Next, we have DPO. It extending tips with DR style correction term to reduce the variance further. When it has low variance when the replying model QR is accurate, reasonably accurate. For theoretical details, please refer to our paper. We conducted some experiments for synthetic and real-world dataset. Due to time constraint, we show only the synthetic results. This is performance as we increase the number of seekers. That is the size of action space. The orange and green lines are our estimators, dips, and DPO. They show lower MSE than other baselines, and the key insight is in the variance. As we increase the number of seekers, the variance also increases, but our estimate much slower in our estimators. This shows the robustness of our estimators in large action space due to the reverse separation. In addition, our estimators show lower selection error rate. So they enable us to pick a better policy well. Next is performance as we increase the positive label sparsity. The red line DM shows suffers from large bias due to the difficulty of match prediction because of the sparsity environment. Since our estimators do not rely solely on the matching label, so they perform better in the across the various sparsity configurations. And in the variance, it shows much lower variance than compared to the IPS and DL due to the two-stage separation. And as a result, our estimator shows much lower MSE than any other baselines. And it also leads to the lower selection error as well. This is a summary. We propose two novel estimators, DIPS and DPL, for matching markets. And in this presentation, we only show the OPE, but in our paper, we also show the OP, off-policy learning as well. And these estimators have better bias variance control than existing ones in both synthetic and real-world datasets. Thank you for listening.
And so these findings look impressive. What are the real-world implications of adopting your method? Could you maybe explain this a little bit in more detail? The real-world implications. So you presented both in the synthetic and in the real-world data set quite some improvements. So how is this then? How can this be adopted for what kind of scenarios?
Our method can be adapted to many matching platforms, like this job matching platform, and our other platform is, for example, dating or room sharing service as well.